Good afternoon. Welcome again. And welcome again to this ARSET webinar on Introduction to Water Quality Monitoring using remote sensing measurements. Today is the final session of this webinar series. And so we had 3 weeks. Last 2 weeks, we talked earlier about water quality monitoring data. We talked about some tools, how to access the data. And today we have 3 parts to this presentation. The first part is a presentation by Dr. Blake Schaefer. Dr. Schaefer is from United States Environmental Protection Agency, or EPA. He's a research scientist working in applying remote sensing data for water quality monitoring. Especially, he's working on algal bloom and monitoring hypoxia in Gulf of Mexico and other regions. This morning, he provided us with a presentation. So we are going to go over his presentation first, which is going to be an overview of water quality monitoring. Then we will have 2 case studies. One will be presented by Dr. Africa Flores. She's from NASA Surveyor Program, and she's going to focus on a lake, inland lake in Guatemala, Lake Atitlán. She's going to show how remote sensing measurements have been useful for monitoring water quality of this lake. Finally, we will focus on a case study focusing on Lake Victoria in Africa. And what we're going to do is go over some parameters which are already existing from MODIS over Lake Victoria, and then Brock Blevins is going to show us a live demo of how to get Landsat data for Lake Victoria and surrounding regions. So that is going to be the outline. And so again, Dr. Schaefer cannot be here to present his talk right now, so I apologize for that. But we will go over what he has provided, and then we'll proceed with the rest of the presentation. And as I mentioned, the outline is going to be in 3 parts, and we will start with this overview part. So let me share Dr. Schaefer's presentation. Okay, so this was provided to us again by Dr. Schaefer, and he can be contacted anytime for more information. So what we're going to talk about is overview of remote sensing, and this is, and in addition to what we've been talking about, this presentation focuses on national and international efforts, which we have not talked before. So these are all the contributors to this presentation from different regions and different parts of the world also. So there is international focus in this presentation as well. Okay, and so we will start with again, what are the use of international community of water quality, and then we will go on to talk about water quality data and tools, where the international community is focusing on. What we see here is that WHO, United Nations, and World Bank, these international organizations are very interested in water quality monitoring, especially for water quality is so closely related to health. And really improving or monitoring water quality and having sustainable water management, that is an important issue both from WHO point of view and also from United Nations. And World Bank also is interested in continued human development, food and energy security, and of course job creation. And for sustained economic and social growth, water is such an integral part in every sector of life that all these international organizations are interested in monitoring water quality. So Here is an example. We have been looking at satellite data. Earlier, it was mostly as shown here on the left-hand side. Remote sensing measurements or sensors were designed to focus on understanding ocean biogeochemical phenomenon and focus on monitoring chlorophyll and other substances in open ocean. And it is recently now that the inland estuaries and lakes are these data, the ocean color data, are also used for inland data. And so there is more work needed to monitor inland water bodies, but these data have been useful for that. So what are some of the issues that international community, both national and international communities, are interested in? So first of all, it is cost of water quality monitoring. There are two parts to it. One is if in situ measurements, they have to be taken, it requires human resources, lab infrastructure, and it can be very costly to have over large water bodies. There cannot be enough in situ measurements, and even if to observe a water body, it becomes very expensive. Another part is again to have humans who are trained to do measurements, so that part also is costly. Now, thinking of remote sensing measurements, they are actually free of charge. All the data sets that we have talked about in previous sessions from NASA, from NOAA, also from European Space Agency, these satellite data are free of charge. There is some cost involved in training human resource to use this data, but then there is near global coverage of this data. And so that is one advantage where, although it's an issue, remote sensing can help a little bit. Another issue is with mathematical formulation or algorithm of using the data. For quantitative information about water quality parameter, in this case, this chlorophyll, there is usually a mathematics involved or algorithm development involved, coding, computer coding involved. And so use of these algorithms, it's not always easy for all the water quality managers or for all end users. It's not very easy. However, in each region, through World Bank or United Nations or other regional agencies or even private companies, they can help in this endeavor. So getting data and developing algorithms, they can be done with help of other people. Another point to keep in mind is atmospheric correction. We talked about this in the very first session, that although remote sensing data are very useful in qualitative fashion, images can help look at water surface. When quantitative information has to be derived, there has to be atmospheric correction applied to the data. Because when satellite looks at reflected radiation, it has effect of not just surface but intervening atmosphere, and almost 70 to 80% signal is coming from not from surface but from the atmospheric part. So that correction is also very important, and that has to be done for quantitative information of water quality. Then accuracy is also very important, that after deriving quantitative data, say chlorophyll, if the value is say 5 milligram per meter cube, one wants to know how accurate it is. Is the real value within plus or minus 1 milligram per meter cube or 10 milligram per meter cube? So how accurate the information is. So validation of data is important. So all these steps, they take time and effort to use data in water quality monitoring. These two somewhat interrelated. One is continuity of measurements. So as we saw earlier, SeaWives and MERS missions, they were providing excellent ocean color data for last decade or so, and both of them no longer exist. They are not providing or any mission observation. So any mission has limited lifespan. So continuity of observations, that is an issue. When a satellite changes or a sensor changes, a new algorithm has to be derived, and that requires a little bit of effort. Spatial and temporal resolutions sometimes change from satellite to satellite and sensor to sensor, so that has to be taken into account. So data continuity is also an issue for using long-term remote sensing data for water quality monitoring. And lastly, it is the support in the sense that for any water quality monitoring project, it starts as a research and then it becomes an applied application for operational monitoring. And that research part or that project usually is supported by for 3 to 5 years, maybe grants or funding from some agencies. And so that also is a limited project, and to make it operational, there has to be a sustained support from local agencies, from NGOs, or from other private companies. So these are some of the issues to keep in mind when using remote sensing data for water quality monitoring. So this is a table, and we've looked at earlier, these are all the sensors from different satellites. This is a pixel resolution for each, and all the water quality parameters available from these sensors are listed, such as chlorophyll and cyanobacterial bloom, etc. So this is a complete table for your information. But to note is that, say, MODIS and WIRS, special resolution is more like 750 meters or 1 kilometer when it comes to water quality products. So if inland lake, say, is very small, uh, less than a kilometer square or just a couple of kilometers, this data are not going to be very useful. Then something like Landsat has to be used, which has 30-meter resolution. On the other hand, MODIS provides 1 to 2 observations per day, so it's a daily data, whereas Landsat has 16-day revisit time, as we saw earlier. And if any rainy day or cloudy day satellite overpasses the water body, surface cannot be seen. So sometimes for a month or a month and a half, there are no images from Landsat. That also can happen. So there are trade-offs between different sensors and different applications. And we've been talking about that, but this provides an overview of existing sensors and what kind of resolution, what kind of parameters are there. We talked about CDAS tool last week, and this is a continuation to that, is that it has a capability to look at several parameters, and the user interface is, graphical interface is quite good, that on hovering on any area, a table appears. That this is hard to read, but you can read it online from the presentation, is that there are latitude, longitude, and values are given. So this is for any given region. This is a quick check from CDAS. This is available from both past data from CVIFs and MERIS and present data from Aqua Modis, as we saw earlier in last week presentation. So this is, there is also ocean color form that can be accessed through CDAS, and any questions can be posted or posed into this user forum, and can be, users can interact and find solutions to their problems. Okay, there is yet another tool, and this is a coast color tool. This provides and the contact is given here. This also provides MERIS data. This is a European Space Agency sensor that is flying on, that was flying on NVSat. So that has a this is a visualization for that, selecting date and selecting region. And so this can provide visualization of water quality parameters from MERIS. This is an important resource for international community. Geo water quality user group is there, and they have a lot of information on this website. There's a point of contact also given, and this focuses on variety of different countries and different water bodies. There are also documents prepared for various issues that can be checked out. And more importantly, GEOS, so part of GEOS is the Group of Earth Observations. They hold a webinar series. Periodically, they have webinars on environmental issues, and this particular is an example of water quality algorithm. These webinars can be found online, and they are also recorded so they can be viewed later on as well. So GEO and GEOS, they provide important information about where water quality monitoring activities are going on, and if there are new algorithms developed. These different news also can be found from these websites. Okay. There is International Ocean Color Coordinating Group. This also has a lot of information, and starting from different bibliography. We've had questions earlier from several end users if we can suggest any research papers or any papers that show how remote sensing data are used for water quality parameter derivation. And these bibliography can provide a lot of documents, and a lot of papers can be found through this forum. Especially these reports from the same site, uh, like this one is remote sensing of ocean color in coastal and other optically complex water regions. Also, there is harmful algal blooms and ocean color. These are the reports found on this website. Going through documents on this, um, these reports can be found, and more information can be obtained about how remote sensing can be used for water quality monitoring. Okay. So there's in that context, International Ocean Color Science Group, they are holding a meeting in San Francisco. This is going to be in June 2015, and the theme is to use ocean color for climate and water quality change, along with climate variability and change. And the secondary aim, but which is really very important, is to create a user community who is aware of ocean color data and how to use it for not only open ocean monitoring, but also coastal ocean monitoring and monitoring inland lakes and estuaries. So this is upcoming. Okay, changing the gear a little bit, we talked about these international efforts. This is a national NOAA site. It is designed specifically to monitor harmful algal bloom in waters. And this website provides information, sorry, about so Gulf of Mexico, Florida, Lake Erie, and a number of regions are part of this network. This particular shows harmful algal bloom where it was high, and so these lakes and water bodies are monitored. So NOAA provides this information for selected regions in over the United States. Okay, this slide is not showing, but this is a diversity too. This connects biodiversity or biological diversity group to Earth observation group. And again, there is more information can be found about inland water quality, especially related to aquatic life. So this website, through this website, end users can interact with Earth observation community as well as biodiversity community, focused more on inland water. Okay. There is a global lake initiative, and this is based on Mary's data, and the website can be found here. This has a lot of there are archival data, there are satellite imageries available, and there is a visual interface to look at Mary's data and look at several water quality parameters from that. In addition, there is a Global Lakes Sentinel services. Now, this GLASS website, this is designed especially to work with future mission data. So when the missions come up, applications are already there. So this is also a combination of scientists and end users coming together to see how future mission data can be used for water quality monitoring. Okay. A regional effort exists, MRSU. This focuses basically on Africa. Coastal Africa as well as inland water bodies can be monitored through this. And this is a central repository of all the information about coastal water quality and other parameters for African region. Okay. Similarly, EOMAP has a visual interface. This also uses in situ data as well as data from Mary's can be found from this site, and they provide number of water quality parameters. They have bathymetry data, in situ data, as well as Mary's chlorophyll and other parameters, especially focused on coastal region in Australia. Okay. This is an effort that is led by Dr. Schaefer, and it's a advanced nutrient monitoring application. This uses CWIFS data, and it will continue with other MODIS and WIRS type ocean color data, and this is focused on coastal region of Florida. This is especially when because of change in land use, and there are nitrogen and phosphorus nutrients, they run off into water, and that has impact on aquatic life, on algal bloom, also hypoxia. So to monitor these, this nutrient monitoring project is being done, and it is focusing right now on coast of Florida. Okay, this is an interesting app that is still under application, and this is especially to monitor cyanobacteria bloom. This is going to be a project to back end of it, which remote sensing measurements will be used, and scientists will be working to come up with near real-time cyanobacterial bloom data, and then through mobile app, different people can access it and see where cyanobacteria algal bloom and algal blooms are happening. So this is a mobile app that is under development. Okay. Um, this sites, Cyclops, this is an interesting concept. This is again, along with coastal ocean data, there are in addition to remote sensing, how to use in situ measurements. So relatively inexpensive optical measurements citizens can take. And that is what this is designed for. And so Citizens Observatory for Coast and Ocean Optical Monitoring. So citizens get involved in taking measurements and then providing it to scientists who can then use it along with satellite data to come up with a better information. Okay. This hydrocolor is also an interesting app. Any water body, just as satellite looks at or sensor looks at reflected sunlight and gets information from that, similarly, our own cameras can look at, take water picture and see how reflected sunlight changes, and that can also help us like looking at color. So this is also, people can get involved, take picture with your own cell phone and upload the picture. So this app also is interesting to check. Information can be, any piece of information we put in can be analyzed. So multiple data sets, in situ data sets, pictures taken by ordinary cameras, sensors, from satellite, they take reflected radiation. All these information can then be used to derive better water quality monitoring. That is the idea behind all these applications. Here is an article. There's a journal. It's called Remote Sensing of Environment, and has a review uh, article, or not a review article, but the whole issue is on water quality. And this particular paper shown here, it talks about what kind of challenges, progress, and future directions are there for inland water monitoring, which is really of a lot of use for most people for drinking water and other water usage. So this is where a lot of research that has been going on, it can be found, and then it can be applied to local regional inland water. Finally, these are all the contact information. Scientists who work with remote sensing and water quality monitoring data in different regions, and they contributed to these slides. Dr. Schaefer, his email address is given here, from EPA. He's the one who put this presentation together, and he will be very happy to take any questions from you via email, and we can also convey your questions to him. But basically, this is where the field is right now, that there are national and international efforts going on, and it back end research and front end application, they're happening everywhere. And there is an effort, as we saw in the conferences coming up, similar efforts are going everywhere, that a user community is developed. They all try using remote sensing data in addition to in situ data from their own local water bodies or estuaries or lakes, and see how these data can be useful for continuous monitoring of water quality. And as we know, it has a lot of applications, for if there are water standards to be observed, or deciding what usage is there for that particular water. All these information can be derived from combination of data sets. So hopefully this information will be useful for different usage, from drinking water to um, maintaining aquatic life, or any other recreational use. For different standards, there are different ways to measure water quality. And the idea behind this presentation was to present all the resources out there which can be explored. And there are some where citizen science is already being done, so that there can be involvement from a lot of people as well. So with that, I will go back to um, my presentation back. Just bear with me for a minute. And actually, what we're going to go is, now we look at two case studies. So next case study will be presented by Africa Flores from NASA Surveyor program. She is going to talk about how she has used satellite data to monitor algal bloom in a lake in Guatemala. So Africa, okay, can you please take over?
Sure, thank you, Amita. I'm going to share my screen for this presentation. And as Amita mentioned, this presentation is for the case study of Lake Atitlán, in which we monitor an algae bloom in 2009, and what were the next steps for that. So at the beginning, I'm just going to give a overview of Servir, and then I will talk about the case study of Lake Atitlán, some general information about the area of the lake in Guatemala, of this lake in Guatemala, and an overview of how to transition from a qualitative analysis and what that entails, a qualitative analysis, and how to transition from that to a quantitative one, which is what we did with Lake Atitlán. In general, Servir is the regional visualization and monitoring system This is a project that is carried out by two agencies, USAID and NASA. We have a network of centers that we work with around the globe. These are the centers. We cover Mesoamerica, Eastern and Southern Africa, the Lower Mekong area. This is our newest hub in this area, and the Himalayas. As well, the coordination office is located in Marshall Space Flight Center in Huntsville, Alabama. That's where I am right now. And well, I mentioned USAID and NASA, which are the partners, the main partners of this project. Currently, we serve 34 countries around the globe, and we work with these regional centers at each of these regions to provide applications, tools, and data, mostly remote sensing data for different applications that go from water quality to disaster monitoring and other topics. There are plans to expand to West Africa, and that's for the near future. And you can find more information about Servir in its website, which is servirglobal.net. So now about the case study, I think that over this webinar we have talked about all the resources that are available to monitor water quality, and this is a very applicable example of how can we use these data sets. So Lake Atitlán is located in Guatemala in Central America. Is a great example of an oligotrophic lake. This means that the water is very clean, which is very weird to find, and it has a surface area of about 137 square kilometers, and the deepest point of the lake is more than 300 meters, which is significant. Is the deepest lake in Central America, and it's surrounded by volcanoes. It's an endorheic watershed, which means that all the water that touches this watershed drains to the lake, and it doesn't have an obvious exit, which also means that has a long stay. All the water that goes into the lake has a long period of stay over there. It has a major source of income in terms of tourism. It's the second most visited touristic site in Guatemala. Around 400,000 people depends on the health of this lake, and the not only for tourism but also is a source of drinking water for the communities around the lake, and also they fish in this area. This is another picture of the lake. To give you an idea how it looks, you can imagine the topography. It has three volcanoes around. There are three volcanoes around the lake. So in 2009, an algae bloom appeared in the lake, which take everybody by surprise. But actually, maybe not everybody. There have several institutions that have been working in this area for a number of years, and they have knowledge of the pressures that the lake faces on the year basis, and some of them are listed over here. There is unsuitable agriculture, where most of the soil in this watershed is not suitable for crops, and there is also unplanned urban development. There is a lack of sewage treatment plants, which is a major problem for this area. And given the unsuitable agriculture in this area, there is a high soil erosion that increases sedimentation into the lake, and also is a cause for agrochemical runoff into the lake. So all of these feed into the appearance, the algae bloom that appeared in 2009, which was the first one to be this large, and the largest algae bloom in this lake. And we start monitoring using different multispectral sensors. Among them, we have Landsat EO1, including Ali and Hyperion, and Aster. So since we use all these satellite resources, it was feasible to have a temporal resolution for saying this way. EO1 was tasked, and we can have a good coverage in terms of time. We monitor this lake for all November and December. We started monitoring at the end of October when the algae bloom appeared. And in the survey website, you can find more information about the analysis. So we only use satellite remote sensing to base our analysis to distinguish algae from non-algae. And since it was a massive algae bloom where we have chlorophyll concentrations higher of 100 milligrams per cubic meter, it was easy to distinguish between what was water and what was the algae. And we use red and near-infrared bands to do that selection. And in this website that is in this presentation, you can see all the analysis performed for this monitoring. As I mentioned, this is an example of a qualitative analysis because the information that we have from the field in situ, it was that the algae bloom was caused by a cyanobacteria. If it weren't because that information was provided to us by the local authorities, we could not even say what was causing this algae bloom or what species was causing it. So that's very important information. And by only having remote sensing, we couldn't have that type of detail. So our detail was more in terms of having there is high concentration and low concentration, but no amounts because we have enough in situ observations to do those assumptions. So this is an example of the qualitative analysis, which was very useful because at the moment we could map what was the extent algae bloom, but take into consideration the conditions of the algae bloom. It was extremely high chlorophyll concentration, and therefore it was easy to use different multispectral sensors because many of them have bands in the red and near-infrared part of the spectrum. And then we wanted to advance or improve our analysis, and therefore we moved from a qualitative to a quantitative analysis. And in order to do that, we needed in situ observations. There are some records of in situ observations in the lake, but they weren't enough to match our satellite observations. Therefore, we needed to start from zero, and we need to take all new in situ observations that could match satellite observations. For satellite, we use the hyperspectral sensor Hyperion that is on board of the EO1 satellite, and the in situ observations were collected by two local institutions in the area, the one university, Universidad del Valle, and the Lake Authority, AMSCLAI. They were the ones in charge of taking these samples, and which span from January to April. This corresponds to the dry season in this area, and therefore, when it's the dry season, there are very low chlorophyll concentrations, and the lake has a very different performance. The water is very clean. Usually the transparency of the water in the lake is from 15 to 20 meters. Well, in the past it was about 20 meters, which is significantly high. That's why it's a great example of an oligotrophic lake. In recent measurements, the highest it has the highest transparency recorded in the lake is of 15 meters, which is still high. If we can think just of the ceiling of the office where we are is about 2 meters or a little bit more. So 5 times that will be 10 meters. So it's significantly high even in these years where the lake faces more pressures. However, that was the time that we were able to collect data, and therefore we have very low chlorophyll concentrations. As we can see, our measurements recorded concentrations from 1 to 10.9 milligrams per cubic meter. That represents low chlorophyll concentration. So in theory, the spectral signature that we were expecting from these measurements is like this green line where we have relatively high reflectances in the green part of the spectrum and an absorption in the blue part of the spectrum, and then the spectral signature fades and we don't have any more information to use. Uh, so that was in theory. This is another picture of the location of the samples. We coordinated with the lake authorities to take the samples at the moment that the satellite image was acquired. Hyperion has a polar orbit, so we knew what was the time of the day that the sensor was going to, the satellite was to overfly this area. And it took several weeks to take this amount of samplings around the lake. This is an interpolation. It is not to show the water quality conditions of one specific day, but is more to show the in situ observations that were used to develop an algorithm that later could be used to monitor water quality, particularly chlorophyll concentration in the lake. Um, so um, current investigations of the current methodologies that are used to monitor chlorophyll concentration in the water bodies use usually three different approaches. One is using blue and green band ratios, and that is used when we have low chlorophyll concentrations, because that's when we have most of the information in our spectral bands. If we have higher, relatively high chlorophyll concentrations, the red and near infrared bands will be more useful. And then there is another approach also for high chlorophyll concentration, which is the spectral shape, that instead of using only two bands, as the other two approaches, uses three bands. And this is based on the peak reflectance. So it uses that band where there is the peak reflectance and the band before and after, which is assumed that there are absorption features in our spectral signature. So these are different approaches because in the satellite remote sensing, we saw that we have different spectral bands that cover different parts of the electromagnetic spectrum. Not all those bands are going to provide us information about one particular parameter in water quality. Therefore, we need to use those bands that are going to give us information for those parameters. And in the case of chlorophyll concentration, usually these are the bands that contain or that capture most of the variance for chlorophyll concentration. And this is an example of an algorithm, or in other words, of a mathematical equation that allow us to model chlorophyll concentration based on satellite remote sensing measurements, where the x in this equation represents the index, the band ratio that I was talking about, whether it is with blue or green spectral bands or using red and infrared spectral bands. And that's the type of algorithm that Ocean Color uses for their products for chlorophyll concentration. And if we want to have an application from a particular area for an inland water body, this is we need to use a similar approach, just that specific for our area of study. So these are some of the processes that were used to select which bands, because we were using an hyperspectral sensor. Therefore, we have more than one blue band, we have more than one green band, more than one red. We have about 10 bands for each part of the spectrum, because hyperspectral sensors give us very narrow bands, and therefore we need to test all of them. We use R-squared to do the first selection, and as expected, since we have very low chlorophyll concentrations, the bands that provide most of the variation in chlorophyll concentration for the lake were those blue and green spectral bands. We have the highest R-squared values over there. And then we have the worst performance using the red and infrared band, which was expected as well. And then we use an analysis of variance to identify which of all those blue and green bands were more significant and would represent even better our variance of chlorophyll concentration. And at the end, for Lake Atitlán, this is what we obtain, that the band at 467 and 559 nanometers represent, well, the variation of chlorophyll concentration. And then another portion that wasn't used to develop the algorithm, another portion of the in situ observations, was used to validate and to estimate the error of these algorithms. And we obtained an error of 33%, which translates to a plus minus 0.26 milligrams per cubic meter. So, for example, if I say that in this there are 5 milligrams per cubic meter of chlorophyll concentration, the measurement is off by plus minus 0.26 milligrams. But then we also need to take into account the conditions under which the algorithm was developed, the in situ observations, that we only have data for the dry season. We only had data for very low chlorophyll concentration. So it wouldn't be appropriate to use these same values when we have an algae bloom event, for example. And that's the same when we use products that are previously developed for a certain area. We need to be aware of how they were developed, under which conditions, and how appropriate is to use it for our particular area of study. So in summary, these are some of the remarks that I would like to make. We need to understand very well our area of study. I know that the conditions of the Lake Atitlán, for example, are not always the same. During the dry season, we have low chlorophyll concentrations. Therefore, the algorithm developed is appropriate over there. But during the rainy season, where we have more sedimentation and runoff, the water quality are very different, and therefore the algorithm development may not be that appropriate. Our error is going to be way higher. And as part of this, remote sensing measurements can be extremely valuable as long as we understand the limitations. We can have a qualitative analysis that still can give us some information, but to only base our assumptions on that information, we cannot have amounts, specific amounts. And if we want to have a specific amounts for any water quality parameter, we need in situ observations. It is critical to have those. So it's also for all that people that works with as managers of water resources for inland water bodies or coastal areas. It is important to share those data sets with the scientific community that is developing these data sets. That's one of the main constraints to expand the horizons of the products for water quality monitoring. And it's also presented in the presentation by Dr. Schaefer. And then lastly, I just want to mention an extra resource that people or scientists from around the world can apply. This is a peer call that scientists around the world can apply to obtain funds. As you can see, water quality monitoring is a topic that is still in research. If you want a specific application for your area study, you still need to do some extra research and do the analysis. It's very different from maybe other applications of remote sensing, and therefore research is critical for this area. So please check this website. This presentation is going to be online, and you need to partner with a US scientist, but you can find more information in the website listed here. And that's all that I have, and this is a specific example of one application that we have worked with at Servir. So that's all that I have for the Servir, Amita.
Thank you, Africa. So we will continue with our next case study. What Africa here was an excellent example of how to use multiple spectral bands to actually and in situ data to derive water quality parameter. In this case, it was chlorophyll. And so now the next case study that we want to show is going to be focused on Lake Victoria in Africa. The idea is that what Africa showed is that you start with raw spectral reflectances, take in situ measurements and derive measurements. Their MODIS-based parameters are available globally, and so we want to present that first over around Lake Victoria. And then the second part, that qualitative monitoring of water, how it is changing, can be done by looking at satellite imagery. So this case study in first part will look at MODIS data. MODIS data from Giovanni and Ocean Web that we looked at last time. And then for the same region, Brock Blevins is going to show how to get raw satellite images, and looking at images, qualitative information can be obtained about changing water quality. So we'll start with this Giovanni website that we covered last week. There is a ocean portal in which there is water quality monitoring portion that we covered last time and last week too. And this shows chlorophyll concentration over Lake Victoria. This is derived from MODIS flying on Aqua satellite. We've talked about this satellite and sensor earlier. This is a gridded level 3 data. This is available at 4 kilometer. And this visualization also is done by using Giovanni options that we covered last time. So this map here shows long-term mean of chlorophyll concentration. So this is July 2002 to December 2013. So mean chlorophyll values can be seen in milligrams per meter cube here. The high end here, red colors, is about 30 milligrams per cubic meter. And within the lake, it is more like 7 to 8 milligram per meter cube. This is again a long-term mean, and it changes from day to day, from week to week, from month to month, depending on conditions in the surrounding area. One thing to notice is again that in coastal area, chlorophyll concentration is high, and this would be expected as there will be a more runoff impact in the coastal region, and there will be more nutrients going in, and more chlorophyll can be detected in this region. What this shows is now is time sequence or time series, a month by month evolution or change of chlorophyll over averaged over entire lake. There is a strong seasonal and interannual variability as one can see. So these data, so MODIS data and past data from CVIPS and MERIS, they can be used to look at past trends or variability and understand any particular region, what is going on. Again, the limitation is going to be with the resolution. This one is about 4 kilometer resolution. So large estuaries and inland lakes can be monitored by using this data. This is also from Aqua Modis, and level 3 data at 4 kilometers shown is colored dissolved organic matter index. And this is similarly a long-term mean map, and there is a time series, and perhaps there is some indication that there is in over Lake Victoria, dissolved organic matter, is it increasing, or there is a slight trend one can see in this region, average over the entire lake. So this tool and these data can provide quick information, a quick history about any lake region or coastal region, and so that is useful. Similarly, if more higher resolution data are required, so we talked about ocean color web last week as well. So level 1 and 2 data can be available from ocean color web. So what's shown here is that there are different sensors. Again, we're looking at Aqua Modis here. There are time from 2002 onwards and dates. So calendar is given, so any date can be picked. Different parameters can be picked, and uh, there are some pre-designated areas given here, and Lake Victoria is one of them. Otherwise, just drawing on the map can also help select a box, but Lake Victoria is given in there. So, and once everything is picked, a swath data has to be found, which we have done here. This is now 1 kilometer resolution data over this region where Lake Victoria is shown here. And let's see if you can see, here is Lake Victoria within this tile. This shows MODIS image, raw image, in true color image. This shows chlorophyll concentration, and this is surface temperature, sea surface temperature, and scales are given here. So this helps a slightly higher resolution data from MODIS, and these data files can be downloaded from this interface here. What to see here is that there are clouds in this image. Sometimes when there are clouds present, when all the black area here and white area here where there is no data, because of clouds, surface cannot be seen clearly. So this happens looking at swath data. L3 data, which is averaged or composited over time and space, provides more continuous information. But so data has to be selected based on application, about the size of the reservoir, and about how much what application is needed. Is it weekly composite is okay, weekly monitoring is okay, or monthly monitoring is okay? Based on that, data can be used. So this showed example of how existing data, these parameters are already derived based on algorithms. So they are available from Giovanni and Ocean Color Web that can be tried for different regions. And so next step is to suppose we want to look at higher resolution images and want to look at qualitative changes in water quality. What can be done? And so higher resolution Landsat data help do that. So Brock Blevins is going to show us how to get to, in this case again, Lake Victoria, how to get Landsat images for Lake Victoria and see water quality monitoring be done with high resolution data. So we talked about USGS tool last week. Earth Explorer provides a nice interface for not only Landsat data, but Ester and EO1 Hyperion data can also be obtained through this. So Brock, to you, and you can show how to get Landsat images for Lake Victoria.
Okay, thank you very much. Can you hear me okay?
Yes.
I'm going to share my screen here. Okay. So what you see here is the Earth Explorer website. This is the home page, available through the USGS website, and you can see the URL up here, earthexplorer.usgs.gov. And complementary to acquiring the MODIS data that Amita showed us for the Lake Victoria case study, for this demonstration, we'll walk through the routine of acquiring Landsat data and all its bands by using this data portal. Before we proceed, however, I do want to point out that although the data is free, we need to log in or register an account with the USGS, and you can do that right here by registering. And it's just very basic information, but I just want to let you know that you're going to want to register and then log in order to eventually download the data that we will be looking for. So I'm just going to log in here real quick. Okay, back to retrieving our Landsat data. So on the right you see the map, a very interactive map. You can grab and pan around the globe to your desired area of interest. You can zoom in, and here's our Lake Victoria. From here we can choose an area that we want to obtain all the Landsat scenes that have been acquired, and we can either type Lake Victoria right here in the search box, and many geographic features around the globe are in this database, and Lake Victoria comes up and we can click that. Alternatively, you can, if it's not in the database, you can choose the coordinates in which you're going to retrieve your Landsat scenes, and you can do that by activating the coordinate tab here, and then you can click on the map in a couple different spots. I'm just going to draw a rectangle here, and as you can see, the coordinates are being loaded into our search criteria. Next, we want to choose our date range, and you can do that down here off to the left. You can either enter your date in here or use the calendar. We are going to choose 2003 through July 2013, roughly the same date range that Amita had showed us with the MODIS data. July 2013. And then I do also want to point out that right next to the date range, you can open up the Result Options tab. And what this is showing us is that the number of records to return is set at 100. Now, however, the records that exist might be higher than that, so we're going to crank this up to about 2,000 in order to make sure we don't miss anything. Next, we can go up to the top and open up the Data Sets tab. This is where we can choose the type of data. And as you can see, there are quite a few to choose from. Quite a bit, actually. What we're interested in today is the Landsat archive. And even within the Landsat archive, we have a couple different choices here as well. We have Landsat 8 and its sensors. We also have Landsat 7, the Enhanced Thematic Mapper, plus with the SLC off. We're going to choose this one. And the reason for that is that it encompasses the date range that we are interested in. Alternatively, you can also choose to look at Landsat 4 through 5 and other ones here if you don't find the data that you are looking for. Okay, from here we can choose a couple different additional criteria in which to narrow down our search. And under the Additional Criteria tab, if you are familiar with the particular date or this path and row of your Landsat scenes that you wish to acquire, you can enter those right here. Also, you can choose the amount of cloud cover in the scene, and right now it's selected as all, but you can restrict your criteria or the search results by the percent of cloud cover of that particular scene that will be returned to you. We're going to set that at about 50%. From there, you can click Results, and this will process slightly and show us all the results that are available for about the 10-year date range in this region around Lake Victoria. As you can see, there are almost 2,000 different scenes that fall within this polygon that we drew here. And off to the left, you have the first 10 displayed, and you can see a little thumbnail of each one. Within each thumbnail, you have some information available to you. One is the ID of the Landsat scene. Second would be its acquisition date. And then you also have the path and row in which that Landsat scene was acquired. So what we can also do is, using these icons next to each result, is you can see exactly where on your region of interest this Landsat footprint occurred. You can also click on and see the actual Landsat scene itself by clicking the second icon here. The third icon is a browse comparison tool. You can select multiple scenes and put those into a window in which you can compare many scenes amongst each other. You can also view the metadata associated with each scene. You can also download your data right here by clicking each download next to the description. You have 4 different choices here. You can click Landsat Look, Natural Color. You also have Thermal Image, where the bands have been adjusted. You can also download the Landsat image with geographic reference. This is really useful inside of a GIS. Now, if you notice the size of these files, these are rather small. All the data, in fact, all the different bands in which we can acquire, will be the level 1 product data. And as you can see, this is much larger than the rest. And you can simply just click on these and it will download to your computer. Some of them will be quite large, especially this level 1 product, and that will be delivered in a tar GZ zipped format. If the level 1 product is not highlighted, as in you can't click on it right away, that means that that image will have to be processed. And in order to process that, you have to first put it inside either a bulk download, which is this icon here or inside the shopping cart. And then you simply go to your item basket here and it will show. You can proceed to checkout and then submit that order. And the first few items, since they were very small and they did not require processing as opposed to the level 1 data product, those will be sent to you rather quickly. However, because of the processing involved for the level 1 products, it might take sometimes a day, sometimes 3 days, but in all reality, I've never really had to wait longer than a couple hours in order to retrieve those. You will be sent an email that looks like this, in which you can click on the links here and then download your level 1 data products. So that's Earth Explorer. It's one way to obtain Landsat scenes, one of many different portals in which you can obtain Landsat data. I encourage you to explore the other data products that are available through the Earth Explorer, as well as Glovis, another data portal, and Landsat Look Viewer, another very useful portal for obtaining Landsat data products. And if you haven't looked at the materials that have been presented through our land management webinar, please take a look at those because we have many presentations and recordings of the presentations that will help you explore further in obtaining land management imagery and data. All right, and with that, I will send this back to you, Amita. Thank you very much.
Thank you, Brock. To the conclusion of this webinar and to summarize what we saw in this entire series, just a few points. This was an introductory webinar, and the idea was to put out all the satellites and sensors which are useful for monitoring water quality. So we started with actual parameters which are already retrieved and available through some tools. So these are MODIS data. They are available both on swath and gridded data. So chlorophyll concentration, color dissolved organic matter, euphotic depth, temperature, and spectral reflectances. These are all available through Giovanni and Ocean Color Web. These parameter retrieval should continue through WIRS, which is a NPP instrument sensor, and currently chlorophyll concentration is available as we saw last week. So these are all readily available water quality parameters that can be checked out in global context where the inland lakes or coastal water. The second type of satellite data we saw was spectral reflectances available from missions like Landsat, so ETM plus OLI imagery available for a long time at higher resolution, like 30 meters or so. And Brock showed Earth Explorer, but there are other tools where these spectral data can be obtained. And we talked about some experimental data as well, which can be obtained from here, which need further processing and algorithm development to get quantitative information, but just images can also provide qualitative information. And Africa provided an excellent presentation that how qualitatively algal bloom was seen in Lake Atitlán, and then later on how algorithm was developed and actual milligrams per meter cube values of chlorophyll was derived. So that is a little involved, but that can be done. And it is a research problem. Regionally, it has to be done case by case for quantitative information. So these data can be used for both research and application for water quality monitoring. We talked about past water quality parameters. They are available from CWIFs and MARIS from Ocean Color Web. So actual chlorophyll data and other organic dissolved matter, these are available on Ocean Color Web for looking at changes that occurred over years. We talked about some experimental hyperspectral data from Hyperion and HICO, and how further processing is needed. These data can be available from Earth Explorer and HICO from Oregon State University, but they have to be requested. They are not as operational as Landsat or MODIS data are. We also briefly talked about a biogeochemical ocean model that NASA has and has a number of water quality parameters in global oceans and coastal regions from this model as well. In summary, though, it is very important to note that in situ measurements are very important. They're critical not only for developing algorithms as shown by Africa a little bit earlier, but also for validation. So if ready-made data from Giovanni or Ocean Web based on MODIS or MERIS or CIVIS are used, then it is a good idea to validate or check out with in situ measurements to have accuracy, to know accuracy of the data obtained from remote sensing observations. So that is also a very important point to keep in mind. And we talked about remote sensing trade-off earlier, that it's not always easy to get high spatial temporal spectral resolutions. So sensor design and satellite missions, they have constraints. So that is case by case which product to use that has to be decided. So there are positive points such as global coverage or near global coverage is there from satellites like Terra and Aqua, but has relatively lower spatial resolution. About 250 meters to 1 kilometer is the highest resolution one can get. Whereas Landsat, EO, these are 30 meters resolution, but then has revisit time that is a little longer. So daily monitoring is not possible, sometimes not even possible, like monthly monitoring is possible. So one image per month or some such availability is there. There are multiple sources of data as we saw. So there is Landsat, there is MODIS, there is CWIFs, there is MERIS, there also VIRS is there. So again, case by case, it has to be explored which data are suitable for what applications. And sometimes data cannot be directly usable. In situ measurements or further processing may be needed if you start with high resolution spectral reflectance data from Landsat or EO1 sensors. So these are some of the things to keep in mind when start using remote sensing data. For water quality parameters specifically, um, it, it is, as we saw earlier, atmosphere and clouds, they contribute so much to spectral reflectances, so that has to be, that effect has to be removed. If there are too many clouds, surface cannot be seen, and then water quality cannot be derived or water cannot be seen. It is just the clouds that we are seeing. So that is one drawback. Sometimes medium spectral band data have multiple water quality parameters contributing to the spectral signature. So change in spectral signature may not be just one parameter like chlorophyll, or could be suspended particles in there, multiple parameters. So then in situ measurements have to be taken to kind of validate what is going on, or further processing may be needed. And over coastal region or even lake region, depending on what the special resolution is, there could be land contamination in this. So it's not just water that is giving spectral reflectance signature. So these issues have to be tackled to get quantitative information about water quality parameters. So, but that said, there are major advantages of using remote sensing data. As we saw, um, in situ measurements have poor sampling in space, and most of the time in temporal resolution is low too. Whereas satellites have uniform spatial and temporal coverage, it has near global to global coverage. So when combined with in situ measurements, remote sensing measurements can be provide very good information about water quality parameters, and these data are completely free. So remote sensing data are completely free. There are tools available, and so they can be used anytime and anywhere depending on what water reservoir you're looking at. So in conclusion, Then we mentioned that water quality parameters, again, this is a research problem or case by case study, lake by lake, one has to study. So for that, NASA has two mechanisms. One is there is applied sciences program has research to application opportunities in which research is done with an objective in mind that the results will be used in operational application, and competitive proposals can be submitted, and funding can be obtained to do this region by region. Another program is NASA Develop program. It's a capacity building program in which if there is a little bit of help needed with data processing or software development or algorithm development, then proposal can be submitted, and student liaison will help end users to work with NASA data. So this is more specific short-term project. This is 3 to 4 year project which requires more effort and it's more competitive. Finally, the ARSET, we are here to provide trainings, both introductory and advanced trainings on a number of areas. We provide trainings in air quality, eco forecasting, water resources, and disasters management. So not just quality, but quantity of water, and that we talk about regional and global water management. So we provide introductory online training such as this one. Advanced training can be requested in which suppose there is a specific product needs to be used for a particular lake or region or coastal oceans in this case. Uh, RSET can prepare training and work with end users to deliver that through advanced webinar. There are online trainings also, I mean, in-person trainings also available. They take a little more planning, but when in-person trainings are planned, these are short, like small group of people work in computer lab, and hands-on case studies are designed so end users actually can go in and learn to get the data for the region that they have picked or pre-selected, and for the applications they have pre-selected. So this is more customized approach to training, but RSET is there, and throughout the year we provide webinars and trainings for these areas. So this is our website, and there is an application area where one can apply for future training, and there is also you will be able to find presentation recordings here. We apologize, we had some technical difficulty and we could not put this information earlier, but you will have second week's information now, and pretty soon we will post today's presentations as well. Finally, there is a homework assignment, and the link is provided here. It's a Google form. So it's an online homework assignment that's due on 31st of September. And those attendees who have been attending all three sessions and one are interested in getting a certificate from RSET will have to complete this assignment by 31st of December, and then the certificate will be awarded in late January or so. Um, this is our listserv that can be joined, and that keeps you up to date with upcoming webinars and trainings. Okay. Finally, we want to thank a number of people. Blake Schaefer, who provided us the presentation, overview presentation, Africa Flores, who helped us put a lot of information together, and she also delivered the webinars in Spanish. Ana Prados is RSET manager, and she helped in various ways. Brock Blevins also has helped a lot in preparing the webinars, as well as working with attendees and looking into registration and putting recordings and presentations for you online. David Barbato has done Spanish translation. They can also be found online. And Kristen Lee from NASA Applied Sciences, she has helped us a lot in, encouraged us in developing this water quality training. Marinas Martins is our helper. She can be contacted for any further information or for homework or certificate or any other material. She's our go-to person for that. And she contacts any of us when any particular issue arises. So with that, we really want to thank you for your participation, and we will be emailing you a survey. This is for your feedback for the webinar presentations as well as material covered. So a number of questions are there, and we'd really appreciate it if you can turn the survey in. It will be sent to you by email. It's an anonymous survey, so we really request you. Your feedback is very important to us. So when you receive the survey, please take a few moments to complete that and send us back. So that will be greatly appreciated. Um, and so this concludes the webinar series today of water quality monitoring using remote sensing observations. And if there are any questions now, we can address those. And as we mentioned, if there are any further trainings that you need or any advanced webinar or in-person training, please contact us through our website and the email address provided to you. So thank you again.